You know, it's never easy. You know, whatever you do, it's never easy. So here we go. Relative acceleration, man. They're really going to take this one down. Okay, let's have a look at that. So this is a lot like relative velocity, but it's got an extra little bit in there because what we're going to do now is we've got relative acceleration. So a sub b now instead of v sub b, it's a sub b is a sub a plus a sub b with respect to a. Okay. So that's what we got. So. Now the thing here is that relative acceleration, just like relative velocity, is caused by rotation. And so it being as you've got an acceleration that's rotating, you're going to have two components there, a tangential and a normal. And I don't really have this stuff specifically up. We're kind of starting in on page 580 is about where we're at. Okay. All right, so the relative acceleration of b with respect to a is going to be a b a n plus a b with respect to a t. So there can be two components of the relative acceleration that we got to deal with. Okay, now another thing here, and this is on 580, this statement here. We went through the whole deal with velocity, that if you have a vehicle moving at a certain speed, v0, and if the wheel that supports the vehicle does not slip as it rolls, you've got two velocity vectors on those perimeter points that are equal. They just often point different directions. So the blue vectors, so these ones are all due simply to the fact that the object's moving to the right. The red vectors are due to the fact that oh boy, close. There we go. The red vectors are due to the fact that the thing is rotating without slipping. And it just so happens that the two vectors are equal in magnitude. So if you want the absolute velocity of any point, you have to sum the vectors. Okay? You can make the same argument for tangential acceleration and the acceleration of a vehicle. Okay, it's the exact same argument. The results are the same thing. So if that vehicle is accelerating to the right, of course, you'd have vectors on the wheel that express that acceleration to the right, but you'd also have rotational tangential acceleration vectors on the perimeter of the wheel. They're equal to the acceleration of the vehicle as a whole, but they point different directions. They're pointing in the direction of rotation as the perimeter of that wheel rotates. And I have this statement here on page 580 there. It's underneath the problem statement. Okay? And it just basically says the relationship between tangential acceleration and the acceleration of a vehicle as a whole is the same as the velocity and the velocity of a perimeter of a wheel. And this holds for wheels that roll without slipping. Okay. All right. So, given that, let's figure out what the acceleration is at point A as that wheel accelerates to the right at 0.6 meters per second squared, and it's got a velocity of 1.5 meters per second. We've got a 0.3 meter radius for this wheel. And we're going to look at that point A, which is 70 degrees up and to the right from the center. Okay. So that's what we're going to look at there as far as the sketches go. So what we're going to do is we're going to use this relative acceleration thing here. So we're going to have A sub A is equal to A sub C plus A sub A with respect to C. That's how we're going to do that, okay? And what we're going to do then is find these different pieces and put them together. So we're just going to find those one at a time. Right now, as we just stated there, the tangential acceleration of the perimeter of the wheel and the acceleration of point C there in the middle are the same. They're both 0.6, and that's given. So that little statement I said basically led us to the fact that AC is equal to AT. Okay? And that's 0.6. Now we also want to find the normal acceleration of a point on the perimeter, and that's v squared over r. We've got the velocity of the wheel is the wheel in the vehicle is 1.5. So the normal acceleration will be 1.5 squared over the radius, and that'll be 7.5. So we're using this wheel rolls without slipping idea here, because what we're saying here is the velocity of a point on the perimeter is equal to the velocity of the vehicle as a whole, and that's 1.5. So if I take v squared over r, I'll get the normal acceleration of that point on the perimeter of the wheel. So what I want to do here then is find the total relative acceleration of A with respect to C, and that will have a tangential component and a normal component as A rotates around C. The tangential is just 0.6, and then the normal is v squared over r. It's 7. The tangential acceleration is 0.6, and the normal is v squared over r, which is 7.5. So what I'm going to do there is I'm going to vectorize this relative acceleration of A with respect to C. I've got the tangential, which is tangent to the circle, so that's down right at 20 degrees. And then I've got the normal going from A in towards the center at 70 degrees. So what I'm doing there is just vectorizing the both of them. So I've got cosine 20 and sine 20 for the tangential, positive x and negative y. And then I've got cosine 70 and sine 70 for the normal. They're both negatives. So I just go ahead and break those two accelerations up into I and j components there. Okay. So, a fair amount of number crunching with this stuff with the vectors, but all I'm doing there is just finding AN and AT. Those are the parts of the acceleration of A with respect to C. And then I'm figuring out what direction they point, and once I've got that, I'm doing the trigonometry to break them up into X and Y components. That's all I'm doing there. Okay. And one new thing here is that AT is AC. They're equal to each other. They're both 0.6. Okay. So are we good with that? So what we're going to do with this is we're going to also get the acceleration of C, which is pretty easy. We're given that, it's 0.6i. And we're just going to add all this stuff up. And that adding AC plus this acceleration with A with respect to C, adding everything up, all the i's and all the j's, will get us the total acceleration vector for point A is what it'll do. And that's what we want. So this one's pretty straightforward. Okay. We can go ahead and do that. So AC is 0.6i plus 0j because the wheel is just accelerating to the right at 0.6. That's the acceleration of that center point, the axle. And then I look at how A rotates around that, and I've got that as a vector. So what I got to do is just add everything up is all I got to do. So I add up all the i's, and I get negative 1.4i, and I add up all the j's, and I get negative 7.25. That's the j. So that's the acceleration of point A. So that's a little bit of relative acceleration there, and it's the same idea as velocity. It just has a little bit more of a complication there in that you have to consider two components to the acceleration of A about C. Okay. And you could do that with vectors as well. I mean, I did it, using trigonometry, but you could do that with vectors too. The normal is omega squared, negative omega squared times the position vector from A to C. The tangential is alpha crossed with R. And you could have done it that way as well if you prefer using vectors. It's, whatever way works is fine. Okay. All right. So that's the deal with that one. And why don't we have a look at 590 and 600? These are kind of full-blown relative acceleration problems. Wouldn't be surprised again if you mechanicals see these again next year. So it's the same linkage system as before. So what we know here based on our previous work with this, and we did this already, this is the one we did relative velocity with. And so, we did that on 540 and 541. And what we found there for this particular problem was that omega, C with respect to B, was 8.8. Okay. And the other piece of information that I've added to this thing is that alpha is 21. Okay. And that's alpha AB is 21, or B with respect to A, I should say, is 21. And then on 540 and 541, we found that omega is 8.8. So what we can do with this then is go ahead and work our way from A to B and B to C. Our goal here is to figure out what's the acceleration of C this time. Instead of just the velocity, it's what's the acceleration. Okay. So we'll work our way from A to B, get the acceleration of B. Once we got that, we'll go from B to C. All right, so the first thing to do is to find the normal and tangential accelerations of B. It's just rotating about A. So the normal acceleration is omega squared R, so that's 6 squared because you're given omega times the 0.46 meter distance. So that's 16.56. And then the acceleration of B with respect to A tangential is alpha R. You're given alpha at 21. R is the length of the linkage. So that's 9.66. So those are the two components of acceleration of B as it rotates around A. And then what we've got going on there is we've got the normal is going from B towards A at 34 degrees. The tangential is making a right angle with the linkage. So if you have your total of 180 there, take away the 34 and take away the 90, what you get is 56. You could just take 90 minus 34 to get 56 also. That works fine. So we've got the normal acceleration going up left at 34 degrees and the tangential going up right at 56. So what you can do then is the trigonometry there and get the acceleration normal in a vector form minus cosine 34, 16.56i plus sine 34, 16.56j. And then the tangential is cosine 56 because the tangential is upright at 56. So cosine 56, 9.66i plus sine 56, 9.66j. Okay. And then what you can do is add those two things together to get the total acceleration of B. And I did that for you down there. It's negative 8.3I plus 17.3J. So that's what B's doing as far as its acceleration. It's just rotating around A, so it's got a combined acceleration of negative 8.3I plus 17.3J. Okay. All right. All right, now once you get to that, what you want to do next here is go ahead and look at the acceleration now of C with respect to B. So again, that's going to have a tangential component at a right angle and a normal component going from C to B. So you find their magnitudes first and then do the vector stuff on them, okay? So what we got for the magnitude of the normal is omega, which we found on 540 and 541. That's 8.8 squared times 0.6. And then, so that's the normal. It goes down left at 17 degrees, so I do the trigonometry on that and get it figured out. And then I do the tangential, alpha r, 0.6 times alpha. 0.6 is r. Alpha, I don't know yet. And that's going to act perpendicular to the linkage. So that'll make a 73-degree angle up left or down right, one or the other. Okay. I went with up left, so that's negative x, positive y. So I got negative cosine 73 for the x component times 0.6 alpha, and sine 73 for the y component times 0.6 alpha. So that gets me a vector expression for that tangential acceleration. Okay. All right, Bill, you got any questions on this stuff? Okay, so what we're doing here, we're just looking at what's happening is as C moves relative to B, and just like with velocity, it's a rotational type motion, the relative acceleration. So we get normal and tangential components. We're just finding out what we can about their magnitudes, and then we vectorize them. And then we just got to string everything together like I did down there about 2/3 of the way or 3/4 of the way down to get our total acceleration equation. So once you got everything kind of worked out, you just want to string it all together into an I and J vector equation, and you solve out the I and you get alpha, and then you use that alpha, plug it back in and solve out the J's. And get A sub C. That's the process on this. Okay, we're good with that. So you get to this equation here, and this thing has I components that I'm going to underline here. and j that I'll leave underlined. So you just go ahead and pull out the i's first, because we have two unknowns in this expression. We got the acceleration of c, which is only in the y direction, so it just has a j component. That's on the left. And then we've got ab plus ac with respect to b. We didn't know what alpha was, so that's an unknown too. So if we run that I equation first, we can solve for alpha. It's negative 302. Just plug that negative into the j equation. You can solve for AC. That's how that process goes. So once again here we got a negative alpha. No problem. Just plug it in as a negative into the next step and you're good. Okay, so don't worry about it if you get a negative. Just plug it in as a negative and it all comes out. Okay. So we're good with that? All right. So on 600 there, we got another version of this. We can do it with vectors too. Oh boy, okay. I'm not, being a little facetious here, but it's part of the job. I mean, it's just kind of the deal. So just use this as a good character building exercise when you're doing this and just learn how to focus, take it step by step. The one thing you can learn from this is don't screw up, just step by step. Don't drop a negative, because I tell these stories all the time, but I spent a week designing a piece of a road as big as this room. And man, if I'd have dropped a negative on Monday, that just would have been a problem when I got to Friday. So, this is just a skill to learn for this way of making a living. Just slow and steady, just walk through, try not to drop negatives, just watch your calcs step by step. The organization really makes a difference when you're working. So I told you that, right? Friday, the guy looks over my shoulder and he says, "Oh man, you're using the wrong base map." I'm like, "Oh man." So that was bad. So that was a week of that pretty much went to nothing. So I had to redo it all. They weren't really organized at that place. So, but anyway, so that's the thing you can learn from doing these types of problems. Even though you're in a hurry, and even though you got to study for a physics test, and even though you got to do this and you got to do that, it's no different when you're working. Just learn how to manage it and work through this stuff. Now we all make mistakes. Don't get me wrong, but try and minimize it. Okay, so what we're doing here, we're getting the position of. So we're just doing the same problem vector style this time. So I've done most of this, so we'll go through this pretty quick. But on your homework, it'll take you a while. So RB with respect to A, cosine 34.46I minus sine 34.46J. So when you're doing the geometric approach, you use 90 minus the linkage angle for the velocity vectors. But when you do the vector approach, you of course use the linkage angle, which is 34, because you want to come up with an expression for the linkage, where B is with respect to A. So it's 0.381I minus 0.257J. Then I go ahead and find the normal acceleration of B with respect to A. It's negative omega squared R. I'm lacking the vector thing right there. There it is. Okay, so the negative goes outside. So negative 6 squared. So 6 squared is 36. So negative 36 is what that would be. The purpose of that negative is to turn the vector around so it goes from B towards A instead of A towards B. multiply it by the vector itself that we just calculated there, and you'll get the normal acceleration vector for the acceleration of b with respect to a. And then to do the tangential acceleration of b with respect to a, I cross alpha with r. Alpha is counterclockwise at 21, so that's a positive 21 for alpha. And just run the cross in whatever way works for you, okay? All right, then I just add up the vectors and I get the total acceleration of b, negative 8.3i plus 17.3j. Same answer as I got on the previous page, just a different way of doing the same thing. Okay? And then you're going to do something very similar for the next step, because the acceleration of c with respect to b is caused by a rotation. And rotations have normal and tangential components, okay? So the relative acceleration is done very much like this. It's going to be a negative omega squared r and a cross, okay? So first thing I do there is I get the position of c with respect to c with respect to b, cosine 17.6i plus sine 17.6j. That's just tracking this vector that goes from b to c. So that's 0.574i plus 0.175j. And then once you got that vector, you take negative omega squared. So the negative, it's 8.8 squared, then you take the negative of that, and then you multiply it through the vector. That gets you the normal relative acceleration of c with respect to b. And then you do the cross to get the tangential. The cross has got a 0, 0 alpha in it. Alpha is counterclockwise, so it's positive. I just always put positive alpha on there, but I think you can put a negative in there and it comes out too. So, but I just put a positive because it's simpler for me. Okay, so the alpha carries through on that cross. So that gets you the relative tangential acceleration. Okay, so again, just pick the method you prefer. There's no such thing as an instantaneous center of acceleration, so we don't have one of those, okay? There's just the relative stuff here. And then once you've got those vectors all figured out, we found a sub b, and then we found a sub c with respect to b. We just pop them all together in a big vector expression, and the solution's the exact same as was done on the previous page. You're just generating vectors in different ways, but you use the vectors in the same way once you have them. So once you got the relative, you just do that and, solve out once you got the whole equation, we got a sub c there on the left, is a sub b there on the right, and then 4 terms for a sub c with respect to b, the normal and the tangential. The alpha is an unknown, a sub c is the unknown. Solve out the I equation first, you get alpha. Throw that into the J equation, you get a sub c. Okay. Oh, Friday, is that when we should do this? I don't really want to. You guys got your physics next week, right? No, okay. For now, we'll just make it Friday. When is it? Tuesday is your physics test. Yeah, we'll just push it back. You got enough to do. So the 30th, let's set the 2nd, I think. Okay, there we go. All right. So we can review for that test on Tuesday, I think, for our test. All right. So hope you all have a good weekend.